Hi everybody, my name is Shiza, and in this video, I'll be analyzing this research paper which is called Top 10 BraTS 2020 Challenge Solution, Brain Tumor Segmentation with Self-Assembled, Deeply Supervised 3D-Unet like Neural Networks. And so the reason why I'm analyzing this research paper today is because I've been looking into doing this challenge for the last few weeks, and I mentioned this in a couple of my other videos, but I've been looking into specifically doing a project within 3D segmentation because I've already done one in 2D segmentation and found that really valuable. So the BRATS challenge was something that I came across. I also came across an EM electron microscopy dataset, which I also made a video on. And I'm thinking to do one of these two projects because this one recently caught my eye and it's really valuable because there's the entire process of, pre-processing the 3D data, making the model, and then a lot of researchers are working on this challenge. So it'd be really cool to like work with some of them. And I currently am working with some researchers. So this is why I wanted to analyze it just to see like, for BRATS 2022 or 2020, my bad, 2020 challenge, what were some of the top 10 solutions and what were some of the techniques that they used that would be beneficial for me to use if I were to do this challenge. So to start off, in the abstract, they said that they trained multiple UNet-like neural network architectures, and they did this on the training data set for the BRATS 2020 challenge. So the 3D UNet is basically this model that's obviously used for 3D images, and UNet is like a really common semantic segmentation model, and they use like different variations of it, which obviously I'm excited to read because I've worked with 2D UNet in the past, which works with 2D images, and then this one is a bit of a level up, like a challenge. And so for the solution, the dice that they had, the dice accuracy was 81%, 91%, and 85%. And this was for the enhancing tumor, whole tumor, and tumor core. So this is a really good example that shows all of these. So over here, where it shows A in figure 1, this is the whole tumor. Over here, this is the tumor core, and this is the enhancing tumor. So for the enhancing tumor, there was an accuracy of 81%. For the whole tumor, which is this one, there was an accuracy of 91%. And for this one, there was an accuracy of 85%. It also looked at another metric to learn the accuracy, which was Hausdorff. And it basically is like the distance between 2 points. That's like the distance between what the ground truth segmentation was and what the prediction segmentation was. And so that's like the Hausdorff metric. And basically, it says over here, these were the scores for it too. I don't want to go too deep into that because dice loss is usually like a really good metric to identify how accurate it is, although like this one is also a really good one. So aside from this, there were very complicated training schemes and neural network architectures that were investigated and will be talked about in this research paper, but it really increased the training time and didn't have that much performance gain, as we'll see like in the results and stuff. So we'll just be looking into different variations and different types of methods and techniques that they use for this as well. They also have their solution open sourced here. And I mean, I'm really looking forward to knowing it because they did, as I said, like they got dice accuracy of 81%, 91%, and 85%, which is actually really good. So in terms of the clinical overview, so this is more of the medical side, they're looking at gliomas, which is basically a brain tumor. They're like very frequent primitive brain tumors, which means that they begin in the brain or the spinal cord, and they're usually found in adult patients, and they can vary in terms of the degree of aggressiveness and prognosis. And so MRIs are used to assess this tumor to find out like where it is to gain more insight into it. And then there's like different sequences that it's converted into. So there's the T1 weighted sequence, the T1 weighted contrast enhanced sequence, and there's a T2 weighted sequence and the flare sequence. So I'll kind of talk about that a bit, although like my focus for this video is like mostly tech. I mean, it's obviously important to understand that there's obviously a biological side to the biomedical imaging that's happening in the research paper. And so tissues, the thing about this is tissues have two types of relaxation times. They have T1 and they have T2. So those are the basic parameters behind an MRI. And so a relaxation time is basically the time to echo. And that's the time between the delivery of the RF pulse, which is basically flipping or disturbing the protons at the same time, and they're pushing it out of like alignment in the magnetic field. So that's like basically the process of MRI is what it follows here. So that's the relaxation time, the difference between the RF pulse, and then it's also finding where what time the receipt of the echo signal is. So this might be a bad analogy, but for me at least, like it worked was the fact like let's say you have an automatic door, right? And it's like one of those automatic doors where you like wave your hand and then it like opens up. So the way I like to think of it is let's say you had the box over here where you wave your hand. So you wave your hand here, that like kind of give that sensor kind of like clicks and it's like, okay, now we have to open the door. So that's like the RF pulse where it like kind of opens the door and it knocks it out of like its original state and it opens. And then once it opens, let's say this is like when it opens, the time where it opens and the difference between the time where I wave my hand and where it's open, like that's kind of like the relaxation time. Like that's the analogy I like to think of. And so those were like talking about the T1 and the T2, which is basically the basic pulse sequences in an MRI. And it shows the difference between the relaxation times in different tissues. So that's T1 and T2. There's also FLAIR. And I did look into this a bit for my 2D segmentation project over here, because FLAIR is basically an advanced MRI imaging sequence. And it shows the areas of tissues of like R2 as very bright. So like you see these ones, and these are like cerebrospinal fluid. Um, so the cerebral spinal fluid is basically darkened, and then the areas of tissue T2 are bright. So you can kind of see that here. And so because of that, like because of this contrast, there's like a you can detect the brain lesion or abnormality, which is basically going to be either dark or light spots that don't look like human brain tissue. And like obviously it's not the fluid either. So this is how you can really tell if there's a tumor or not. And the FLAIR sequence just really helps enhance that process. So then we look into this page as well, which is basically talking about how there's 4 distinct tumoral subregions for this. So this is also, it shows it right here. So this is part D, and it shows, first of all, the enhancing tumor. So the enhancing tumor is, here, let's see, the edema, the enhancing core. So this is, oh, so this is the enhancing core. So this is what it means. It's kind of similar to that. So this is the enhancing core, the blue part. We also have the edema, which is in yellow. We have the non-enhancing solid core, which is in red. And then we have the necrotic or cystic core, which is in green. You obviously don't need to know these terms, at least for me, like I'm focused more on the segmentation. So I didn't need to know much about that. But it had these areas and then it clustered it into these 3 segments over here. And it does talk about this too, the whole tumor, the tumor core, and the enhancing tumor. So those are the 3 components. So then we look at 1.2, and it says that the challenge was split into 3 different tasks. There was a segmentation of different tumor subregions. There was the prediction of patient overall survival of preoperative MRI scans. So basically like checking if they're going to survive or not depending on the MRI scan. And then the evaluation of like how uncertain or inaccurate the current manual segmentations are, because that's like the status quo. And so we're segmenting out the enhanced tumor, the tumor core, and the whole tumor we're in the brain. And the 2 main metrics that they used for this was, first of all, the dissimilarity coefficient, which is commonly used. We also did use the Hausdorff distance. So for the dissimilarity coefficient, this is the formula. And over here, you're multiplying 2 by the true positives, which is basically how many voxels, which are like, if you think of pixels, which are 2D, voxels is basically 3D pixels. You could think of it that way. And so 2 times TP over 2 times TP plus FP, which is false positives, and then false negatives. And then we also have the Hausdorff distance, which I also talked about. And it says that it helps the training a lot because even if one single voxel is far away from the ground truth segmentation, the Hausdorff distance will be high. And so it really helps to evaluate, like, is this model actually working, or is it like just being not real, or like it's doesn't have like a proper accuracy. So the Hausdorff distance is like very reliable and helps training a lot. So that's what it's trying to say here. In terms of the method, so they did train multiple neural networks using independent training pipelines, and this was the architecture that they used. So they had an encoder decoder architecture, which really, it's basically inspired by the 3D-Unet architecture, and it's quite similar to it, except there are some differences that we'll talk about too. So what I'll do is I'll keep this model on the screen, and I do have like a printed copy of the research paper, so I'll like talk a bit more about that. So all convolutions, so here like you see this conv arrow, like these blue ones over here in the middle, all of them are followed by a normalization layer and a nonlinear function, which in this case would be a ReLU activation function. That's commonly used in segmentation tasks too. So there's group normalization, which is basically dividing the channels into groups, and then you're normalizing the features within each group. So it's like you're normalizing within each group, and then instance normalization is similar, but it's for every single instance. So it's normalizing all the images separately, and we're using that instead of batch normalization, which is basically taking batches and normalizing them using mean and standard deviation. And the reason why is because in this train set, there was a small batch size, and they thought that group normalization and instance normalization would be better. And the decoder part, which is this downstairs step, is basically having 4 stages. So 1, 2, 3, 4. And it had two 3x3 convolutions here, as you can see. And the first convolution, obviously, you can see that it increased the number of channels from 4 to 48, but then it stays the same here. And that's what usually happens in a UNet model too. So it's, similar to that. We then have a max pooling 3D layer, which basically downsamples the image size. And then from there, that happens a couple of times. After the last stage, we also have over here a dilated convolution. And this is basically using the detection of fine details by processing the inputs at a higher resolution. So it's over here. So you can kind of see the dilated convolution. You see that how there's like these spaces in between. Like this is basically, if a dilation rate is 2, which it is in this case, then the spacing would be 1. So this is like the kernel that's going through the image. So that's like a visualization of how dilation works. We also have concatenation over here, and then we have the encoder. We have the encoder and the decoder. So my bad. I think um I think the research paper might actually be wrong. Yeah, I think the research paper might be wrong because, yeah, it is wrong because this part is the encoder and this part is the decoder, but it referred to this as the decoder, which is not correct. So this is the encoder and this is the decoder. So the research paper is wrong, and I pointed that out. Wow, okay. So this is the encoder, and then for the decoder, you have the upsampling layers over here. It's quite symmetrical actually. And then you have the 3x3 convolutional layers, you have the concatenation, you have the upsampling 3D. It's kind of similar. We also have here deep supervisation, and it does talk about that if we go later on. And we will talk about that. So it does also mention that 3D attention units were also trained, so like having variations. I feel like just having the 3D, like as I learned later on, like the results for just this model that they explained right now, that was pretty good. So if I was looking to do this challenge, I wouldn't have to look at 3D attention units, but it depends. Like there were some parts where 3D attention units did help, and we'll cover those as well. Then we have the loss function, and this was basically dice loss, and it's computed batch wise and channel wise without weighting. Okay, so we don't need to go too deep into that. And then we have deep supervision, and deep supervision was basically performed over here, as you can see. So over here, and it was performed after the dilated convolutions at the bottom of the network. So you can see one's here, and one's here. And deep supervision is basically the fact that multiple segmentation maps, they're generated at different resolution levels. So this resolution level, all of these are different. And so after each stage of the decoder, except the last one, because that's like the actual segmentation map at the end, we did that by adding an extra 1x1 convolution layer, and then they had a sigmoid activation function, and so they had 3 auxiliary losses as well for all of these, so that it was easier to compare, like after the features were extracted within these, and like the resolutions being different, like how was the loss impacted. So that also gives a lot of insight. What else did we talk about? We go down to image processing after that. So image processing, the thing is, it talked about how, first of all, they changed the range of the values of the voxels. That's one thing they did. They also cropped the image as much as possible to contain the whole brain. So there might have been spacing on the outside of the brain where they just cropped it as long as the whole brain shows, and then they just like resized it to 128 by 128 by 128 voxels. And then that was basically the pre-processing. So then they also had data augmentation, and they had two different pipelines that they used. But I'm going to be going through pipeline A just because like there's some parts where there's repetition. I don't want the video to be longer than it already is. So for pipeline A, to prevent overfitting, data augmentation was basically used. They rescaled the value between 0.9 to 1.1. They also noised it with Gaussian noise, and we do have a diagram here. So this is like the noisy image with that particular data augmentation technique. They also did a random flip of each spatial dimension. And then another thing that happened was that the input channel dropping was done. This part, I'm actually confused by what they mean. I'm assuming that it has to do something with like dropout and regularization, but I'm not completely sure about that. And I tried to find some information on the internet, but it wasn't really there. So that was basically the data augmentation. A bit more about the training. They used a five-fold cross-validation. So I looked into cross-validation, and this was a really good article. So if you have K cross-validation, this is how it goes. So you shuffle the data set randomly, then you split the data set. So let's say it's a training data set, as it is in this case, you would split it up into K groups. And then for each group, you take the group as a whole out, or the test data set. So I guess like the test data set, and then you have to take the remaining groups as a training data set. But this doesn't really, I don't know if this was applied to the training or the validation, but basically it's just saying that you're finding the training for like each group, and then you're comparing it all to see like what was the average. And that's how you like cross validate it, right? You see like in this group what was the accuracy or loss, what was the accuracy and loss in this group for K groups. And so there were 5 groups in this case. So that resource might not have been the best in the explanation, but essentially you shuffle it, you split it into 5 groups in this case, and then you find the accuracy or the loss for each one, depending on what the researchers wanted to look at. And then from there, you like cross-validate it. So that's basically what it's trying to say. For pipeline A, it said that for each fold, it trained for 200 epochs with an initial rate of this much, and then there was a cosine decay after 100 epochs. So this is what a cosine decay kind of is. So like if it's going for 100 epochs, so let's say it goes up to here, it would like have that decay over here. So this point would basically be shifted here. That's what it's trying to say with 100 epochs. So that's like how the learning rate would work. You also have the ranger optimizer with a batch size of 1. So again, this is why they didn't want to use batch normalization, because the batch size was so low. It's literally 1. The ranger optimizer is basically a combination of the R-atom and look-ahead optimizer combined. Although I'm not sure if this worked out in their favor or if they looked at other optimizers as well. They don't talk about that. So I'm assuming that this might have been the most efficient one used. They also said that the validation step was only performed every 3 training steps. And I found that really interesting because, I mean, it does reduce total computation time. But in my 2D segmentation project, what I did was that after every training step, after every training epoch, I would just do the validation too. And so obviously that took a lot more time. So I actually really find this interesting, and it's not that hard to change after like, okay, let's do it after each training, or let's do it after 3 training steps. I don't think that's really hard to change. So I'm definitely going to look into that too. So then it talks about like different things that they did in terms of like, increasing their accuracy. I could talk a bit more about this, and I do have some notes here, but I feel like for the sake of time, it's actually not that important. It's just important to note that like in the end, there were some techniques that they used. For this one, it was more like, I guess I could kind of briefly touch on it. It's like you had 200 epochs, and then you used a weight averaging procedure, which was really beneficial, they found. And then for another 30 epochs that they did, which was again evaluated 5 times for a total of 150 additional epochs, which would be again additional 150. The initial learning rate was restored to half its initial value, and then from there they trained it to. They used the atom optimizer for this without using weight decay, and it just talks a bit like about the methods. I don't want to go too deep into that, as I mentioned, but I could, um, if there was more time. And then another thing that was common, they talk about like, float 16 precision and stuff like that. That's also not very important. It's more like if you're getting to the actual code, like these are the specific techniques that they use. So I'm not going to touch too much onto that. For the inference, so inference was basically performed in two paths. So the first one, and this again, this part was also wrong because I looked at another research paper and it talked about something else. So for this one, the first pass was that the models available from each pipeline were assembled separately and then they were averaged. So that's the first pass. The second pass was that they created two label maps for each case, and label maps are kind of like basically the prediction. Like if you have, let's say, a chessboard and you have like label maps, you would be like, this is the pawn, this is the rook, this is the knight, etc. And so that is the second pass. And then they also did say that for every single fold, um, they used, there were like three different models, right? So there was a 3D-Unet that had like the attention version, the one that was trained on an unfiltered version of the training data set, and then one that was trained on the subset of the training data set where the cases were high dice loss. So this is like the filtered version of it. And then this is for pipeline B. Again, we're not looking too deep into that. I don't want to go too much into first pass and second pass because I did give a high level overview. And this again is mostly like, okay, how can we specifically tailor it to get an even higher accuracy? So first pass, second pass, don't need to worry about that too much. This is very important because now we're actually at the part where it's like, okay, well, now we have the validation and now we have the testing. So how good is the model actually doing? Um, so over here, this is what it shows. So this is the dice. This is the dice without the second pass. And this is sensitivity, which is basically total positive over the positives. Sorry, the true positives over the total positives. So the true positives are basically like how many were actually positive, how many voxels were positive, and total positive or true positive over total positive. And total positive is like how many voxels were positive. And then specificity is basically similar, but it's for negative. So true negative over total negative. Sorry, that's kind of like a tongue twister. So true negative is like how many voxels were actually negative, and the total negative is like how many in total were negative, how many voxels. So over here, this is what they found, and they did talk about like it's really not that bad. I mean, like you can see like 80% accuracy, 80% accuracy. It's for the enhanced tumor, whole tumor, tumor core. What they did understand is like from the second pass and the first pass, they did realize that the whole tumor for like the dice metric was higher in B, and so um they hypothesized that the models from pipeline B were better for predicting edema, which is again like a subsection of the tumor that we looked at over here. The edema is in yellow, which is like I guess the whole brain tumor. So you can the whole tumor. So you can see like um, how it differs in this as well. So then after this, we go on to the testing data set. And we're almost done because the results over here, this is what allowed them to be in the top 10 teams for the segmentation challenge. But then again, as it says here, there was a big difference between the Hausdorff metric, between the testing and the validation. You can see that over here, right? Like this is different. And then if you look up, this is also very different. But then if you compare these ones and you compare these ones, they're actually quite similar in the validation and the testing. Um, Aside from that, they then talked about the discussion for this, and that's like where they kind of like concluded it, even though there was a conclusion. Like this part was the one where you're like, okay, this is gluing everything together. Basically, they said that the challenge, the solution actually like was pretty good for them, even though they didn't use like a lot of different variations, and they could have used like different types of residual connections, which were basically the concatenation ones. They could have used dense blocks. They could have used more recent neural network architectures that have like that bottleneck. They could have used semi-supervised settings. They could have done a lot of things, but even without them, like they got a pretty good solution. They got a pretty good result. And then they also did actually try those refinements, but it didn't really help them so much. And so obviously an important thing to note is like you might not want to overcomplicate stuff, but just make sure that you are overcomplicating. Because what if like adding those things actually helped? Well, obviously that would be beneficial in their favor, but it's always better to test it out to see like if it would actually help or not. And if it doesn't have a significant thing, if it just increases the training time and stuff like that, then you have to think about the trade-off there. Um, there was, again, as I mentioned, like the training time, there were GPU memory constraints, and it's a big problem in the industry as well. So, GPU memory constraints was a big problem for me even because like in my 2D segmentation project, like I didn't have enough RAM, I didn't have enough GPU. And so I'm just thinking like if I'm doing 3D now, like what memory would I even have? Um, so that's a big problem that even I have to do um, and like figure out. So another thing they did mention is the stochastic weight averaging, and I kind of mentioned this before, but it's basically averaging the multiple points throughout the stochastic gradient descent stage. And it said that it was the most notable refinement that they used. So obviously it was really beneficial, and it's probably going to help in my experience as well. Then it starts talking about the conclusion, which obviously is really small compared to the discussion. But if you think about it, like this is amazing. The fact that their model is actually kind of simple really surprised me because I thought it would be so complicated. Like I looked at an electron microscopy data set and it was so complicated. It had a 2D to 3D model plus the 3 by 3 by 3, like a spatial pyramid. It had a bunch of things. It had a bunch of refinements. But for this, like they got a really good accuracy and it wasn't even that complex. So, I mean, I just found this to be a really great research paper to read and I really got a lot of insight from it. So I'm really glad that I read it and hopefully you can stay tuned to my journey with this BraTS challenge. Let's see how it goes.